Alright, this is our second problem from the problem set on non-condensable gases from chapter 11. Let's try our way to work through it. So we're told the pressure is 1 bar, the relative humidity is 75 degrees C, and the dew temperature is 25 degrees C. Right, and so the key is we're being told it's the dew temperature. What's the mole fraction of water vapor in the air? So it's Y1. What's the temperature? And then looks like we have more of a mass balance problem, right? So let's look at A first, okay? So in A, we're asked to calculate Y1, okay? And so if I were just to think about relative humidity, okay? So relative humidity, so my relative humidity, RH, is going to be Y1P over P1 sat. Okay, so if I look at what's given in the problem statement, we know P. We're given the relative humidity, but we're not given Y1 or P1 sat. Okay, and you know P1 sat again is one and the same as T, right? Because P1 sat's only a function of T. So I don't know Y1 or P1 sat, and so in A we're asked to solve for Y1. Okay, so in order to be able to solve for Y1, that means I need to be able to calculate P1 sat, or I need to know what's the temperature. All right, so how am I going to get the temperature? Well, if I look at the problem statement, it tells us that the pressure is 1 bar, relative humidity is 75%, and the dew temperature is 25 degrees C. Okay, so what does that mean? All right, so remember when you think dew temperature, okay, dew temperature is looking at case of relative humidity is equal to 1. Okay, so if I'm considering my dew temperature, okay, that's going to correspond to relative humidity of 1, and that would be Y1P over P1 sat. Okay, and so we're told that the dew temperature is 25 degrees C. Okay, so at 25 degrees C then, okay, I have a relative humidity of 1. Okay, so from the problem statement, right, we know P's given, okay, our dew temperature is 25 degrees C, so that means at 25 degrees C we have a relative humidity of 1. So once I know 25 degrees C, that allows me to calculate P1 sat, so all that's left is Y1, right, so that means I can solve for Y1. So in A then, okay, I would solve for Y1, and Y1 would be equal to the vapor pressure at 25 degrees C, okay, which we're told is the dew temperature, okay, of my system divided by P, right, where we're given P. Bam. All right, so basically, again, you know, we have the system that's at 1 bar, has a relative humidity of 75 degrees C, and we're given the dew temperature. So what that means is that if I were to take my system and cool it down to 25 degrees C, that's where water would be able to begin to condense out of my vapor stream, where I'd have a relative humidity of 1. Okay, cool. Okay, then in B, what is the temperature? Okay, well, looking at what we wrote here is now in 8 we just solved for Y1, so the only unknown now is P1 sat. Okay, so in B then, okay, when I'm asked for temperature, right, when I think temperature, I think P1 sat. Okay, so relative humidity again, drop my pen, relative humidity is equal to Y1P over P1 sat. Okay, so now I know Y1, I just solved for it in A, I know P, we know relative humidity, it's 0.75. So I can solve for P1 sat. P1 sat is equal to Y1P over RH. Okay, and so then the idea is if I know P1 sat, I know T, right? If I calculate P1 sat, I could go to my steam tables and find the temperature for which I have that corresponding vapor pressure of water. Remember, P1 sat's only a function of T. Or equivalently, if I had an Antoine expression, I could solve for T. Okay, so in B, I would get T by calculating P1 sat, and then solving for the T, I need to get that vapor pressure. Okay, cool. And so you see, we keep working with the same expression. It's just a matter of knowing what the heck we're being asked for. So C, Your dehumidifier removes water vapor from air by cooling the air to 12 degrees C. What fraction of water vapor is removed from the air? So basically we're going to take our stream from A and we're going to cool it down to 12 degrees C. And we're asked what fraction of water vapor is removed from the air. So of the water that we started with, right, I'm taking this as how much has been removed. All right, so what'll happen is if I have this stream, okay, I cool it down to 25 degrees C. When I cool it down to 25 degrees C, that's my dew point temperature. Okay, that's when water will begin to condense out of the vapor phase. Okay, so at 25 degrees C, at the dew temperature, I have a relative humidity of 1. What will happen is if I keep quenching the temperature, okay, I'm still going to end up with a saturated vapor phase, right? I'm going to have a system with a relative humidity of 1, right? That's going to be at coexistence with my liquid phase. It just means that more and more water is going to be removed, right? Because the vapor composition, or the Y1 that my vapor phase can hold, is going to decrease. Okay, so I'm going to remain at a relative humidity of 1. It's just the amount of vapor that actually comes out is going to go up. Okay, so let's take a look and play with this. Okay, so let's just kind of play with C here for a second. Okay, so let's think about this humidification process. Okay, so I have some inlet stream. Okay, we'll call this stream A, my inlet. It can be at some, say, flow rate A. All right, we take a basis of, say, 1. Then Y1A we calculated in problem A. All right, so I know that. P, right, we're given the pressure. Right? Yeah, and then we solve for the temperature of A and B. Right, so I know TA as well. Great. Okay, and so what were to happen if I were to cool my system down to a temperature of 25 degrees C? Okay, so I'm going to cool it down until I get to 25 degrees C. Okay, so what'll FB be equal to? Okay, what is Y1B equal to? What is, and let's just write down PB and TB. Right, presumably the pressure would stay the same. Right, and so if my inlet pressure is known, then PB will be known and presumably just equal to PA. Okay, but I'm going to cool this down to 25 degrees C. Okay, so what's so special about 25 degrees C is we said that's the dew temperature of our mixture, right? And so if I'm cooling down to 25 degrees C, okay, then Y1B is just going to be equal to Y1A, right? Because all we're doing is that here, okay, I have a relative humidity of 0.75, okay, and so all that this dew temperature, asks is, what do I have to change the temperature to get a relative humidity of 1, okay? And so, the vapor composition is actually the same, right? It's just like dew temperature when we look at a TXY or PXY, right? It's a theoretical limit in which water begins to, condense out. Okay, cool. Okay, so what we're going to look at here, though, is what if now I were to cool this system down to 12 degrees C? Okay, so what if I were to cool this down to 12 degrees C? Okay, what's going to happen? Okay, well, all right, and if I look at the question again, it wants to know how much water is going to be removed. Okay, so what will happen is if I quench it down to 12 degrees C, so I know 25 degrees C, I'm at saturation, right? I'm at my dew temperature. So if I continue to quench it down, I'm still going to be at a relative humidity of 1. Okay, so basically, if I look at my relative humidity expression, which is Y1P, okay, now this would be Y1B, okay, over P1 sat of B. Okay, and so now we know the relative humidity is going to be equal to 1. Okay, pressure, right, is going to be the same as PA. Pressure's known. P sat B, we can go and look up the vapor pressure at 25 degrees C, or 12 degrees C. Okay, and so what do we have? And if you were to plug in 25 degrees C here, and then solve for y, you would just get that initial y we started with, right? Because, well, that's how we solved for the temperature to begin with. Okay, but to solve for y1b, right? Y1b, okay, would be equal to P1 sat at B at 12 degrees C over PB. Okay, so if I cool it down to 12 degrees C, here will be the vapor composition of water and my vapor stream at saturation. And so then if I want to solve for FB, how do I want to, how am I wording this now? All right, now I got to pause for a second to make sure I have this right. Okay, so that would give me Y1B. Yeah, so basically any water removed from the vapor phase is going to be, would come out as liquid. Okay, and so what I need to, draw this picture as is here's my vapor stream. Okay, but then I'm also going to have some condensate. Okay, which is going to be, we'll call this stream C. Okay, this would just be pure liquid water. Okay, and so this would have, mole fraction of water of 1, right? It's going to be pure 1. So if I were to write out my mole balance, okay, I would know that FA is going to be equal to FB plus FC. Okay, and then component mole balance. So I should have Y1 in A times FA. Okay, I assumed FA was 1. I know Y1A, so I know both of these. And then Y1B, I just computed, times FB, which is unknown, plus it's X1C times FC, but X1C is just 1. All right, so I get two equations with two unknowns. So I can solve for FB, and I can solve for FC. Okay, so if I want to solve for FC, right, that's the amount coming down as liquid, which is how much water I would remove. FC is FA minus FB. So plugging that in, I have here the FC. Okay, and actually I want to solve here for FB is what I want to plug in. FB is what I don't care about for now, so this is just FA minus FC. So I can rewrite this as Y1A times FA is equal to Y1B times FA minus FC plus FC. Y1A times FA is Y1B FA minus Y1B FC plus FC. Okay, so just to group terms, if I were to bring this over here, okay, that would make sense because I know Y1A is going to be greater than Y1B. As I cool down, Y is going to decrease. I'm not going to be able to hold as much at saturation. So if I bring this over and collect terms, I have FA times Y1A minus Y1B be equal to FC times 1 minus Y1B. Okay, since I just want everything on a per mole basis, right, per mole of A, then FC over FA would be Y1A minus Y1B divided by 1 minus y1b. Okay, and to be complete, right? What is y1b? Y1b is just P1 sat at b over PB. So, yeah, so this would tell me how much water I'm condensing and removing. Okay, and since y1a is going to be less than 1, this is going to be some fraction of that initial stream. Okay, yeah, so I think that looks right. Okay, so basically we're cooling it. So 25 degrees C, that's when water begins to condense. If I were to continue to decrease the temperature, I'm still going to have a relative humidity of 1. I'm still going to have a two-phase system. I'm going to still have liquid water at saturation with this air-water mixture. But it's just, why one's going to decrease because my air is not going to be able to hold as much. And so as the temperature decreases, it just means more water is being removed from that vapor stream to remain at saturation. Okay. Cool. Then D, what's the due temperature of the air at the exit of the humidifier? Okay. Well, so was this D or E? This was D. E just means he's just asking you to state all your assumptions and justify your calculations. All right, so when I look at D, okay, D just wants the due temperature of stream B. Okay, now when I see due temperature, okay, all that means is at what temperature do I have a relative humidity of 1? Okay, so what temperature do I have a relative humidity of 1? Okay, relative humidity again for B would be Y1B times P over, now this would be P1 sat B at T due. So I know Y1B, we calculated that. I know P. So P1 sat B, all right, at T due, right? So I'm looking for the, I don't know how best to write this if I'm looking for the dew point temperature. So I would look for when this, my vapor pressure, would be equal to the partial pressure of B in my vapor phase. So I would calculate Y1B times P, the partial pressure of water. Okay, I calculate the vapor pressure at the dew point, and then I go to my steam tables and I look up that temperature. Okay, now this does seem a little odd if I haven't goofed anything up, because the dew temperature would just be the same 12 degrees C, all right, because we're assuming that the system has a relative humidity of 1 at the exit. So unless I've overlooked something, then D should just be 12 degrees C, right? Because we're assuming that we're at saturation at that exit. Okay, cool.